And welcome back, everybody, after a break to talk about security program and policies, but this time in the context of cryptography this week. So we're only going to be covering a portion of Chapter 10, starting on page 310 and following. So in this effort, we're talking about cryptography, as I mentioned, and that comes from the Greek word kryptos, meaning hidden, and graphia. Sure, I didn't say that right. Graphia meaning writing. So it's hidden writing, right? And that is going to give us confidentiality, integrity, and authenticity or non-repudiation in the process. So it's really kind of an exciting process. Those are in the bottom line, if we get nothing else, that we understand that there are three purposes to cryptography in total. One is encryption, and that's what we most often talk about, and that's going to ensure that confidentiality. Then we're also going to get digital signatures. So digitally signing ensures that authenticity or non-repudiation that we're looking for. And then finally, hashing is going to ensure integrity, that the data remains unchanged, that it wasn't modified, right? So the data can be hashed, right? And that provides the integrity. And that's going to be used, for example, in forensics. Okay, good start to the conversation that we're having here. So for the objectives for this week, notice most of them grayed out are going to be covered next week when we talk about the systems or software development life cycle in that process. But we're sticking today with the bottom two, cryptography and policies. Again, pages 310 and following of Chapter 10 in the literature. So the system security requirements, right? So this is really the point of the week 8 discussion when you look at this slide, right? Or the SDLC discussion, right? And so SDLC is this overarching umbrella of systems development lifecycle. A major piece of that is also known as SDLC, software development lifecycle, and a portion of the software development lifecycle is the software testing lifecycle, right? And so these are related terms, sometimes at this level used synonymously when we're talking policy. But in terms of SDLC, we were really talking about system security as we build our applications, right? And a lot of times we'll hear it discussed in terms of DevOps, right? Which is an important variation of that is called Devsecops, right, where you incorporate security into development and operations. And so the two main benefits of DevSecOps are speed and security. So development, your application development gives us speed. That's its point. And speed with quality, right? Security portion of DevSecOps gives us the security piece to that application we're building, and operations ensures the software stability so that it can be used in production. So development teams deliver better, more secure, faster code, and therefore cheaper code, right? Using this developmental approach that we talked about, that we talk about in SDLC. And we'll use a process in the development lifecycle that incorporates a waterfall project or an agile project as a way to manage it. So basically, DevSecOps helps bring down the vulnerabilities. It maximizes any test coverage for quality. It intensifies the automation of the security frameworks that we've been discussing throughout this course in policy. And so it ultimately gives us immense scope of bringing down any cybercrime related incidents. And it helps us intensify security, auditing, and monitoring, all important pieces in policy development. Now, with cryptography, encryption is really the conversation of plain text, of converting plain text into what is known as a ciphertext, right? And so we use an algorithm which is called the cipher, a cipher. So a ciphertext is a text that is unreadable to a human or a computer. When I decrypt something, or decryption, that's the inverse now, and that's the process of turning the ciphertext back into this readable text. So encryption and decryption require the use of a secret key. The key is a value that specifies what part of the algorithm to apply, in what order, and what variables act as the input. And when we protect the secret key, that's generally referred to as key management. Now, we want as part of our process. Now, so here's kind of a summary then of some key terms that you need to know in this lesson. Cryptography, encryption, decryption, plain text, ciphertext, key, and algorithm, which I just went over. But pause the video and review this at your leisure. Some really good summary of terms here. And so those summary of terms lead us to the question, okay, from a policy perspective now, what makes a good crypto system, right? And a good crypto system is going to involve these key aspects right here. High key space, right? So the total number of possible keys, a higher key space is better. It's more secure. High work factor, right? What's the effort and time needed to break a crypto system? High diffusion, high confusion, and high obfuscation. Obfuscation is making it hard to understand the encryption process. It's really tied to this confusion that we create. Sometimes, if we're not careful and we haven't architected our network properly, we end up obfuscating ourselves, which is not the goal. Anyhow, that was meant as a joke, but it is also kind of true. All right, so now continue. Remember I said cryptography was about encryption, but it was also about hashing and digital signatures. I'm getting those three things from cryptography. So when we want to ensure that a message has not been changed in any way during the transmission, we call that message integrity. And so hashing is actually the process of creating this numeric value that's going to represent the original text. So a hash function, and sometimes we could use as a hash function a SHA or MD5 are hash functions, those algorithms, that takes a variable size input, and what it's going to do is produce a fixed size output. So the output is referred to as a hash value, or sometimes it's called a message digest, or even a fingerprint. So when we download something from the internet, there are programs you can download to check. So if you download something, it should share its hash value. And what you want to do is reshare the hash, recalculate the hash value, and compare the two. And if they're the same, what you downloaded is what was intended to be downloaded, that nothing was added in the middle, like a man in the middle type thing, right? So then we have digital signatures. So digital signature also uses a hash value, right? That message digest. But and this has been encrypted by using the sender's private key, right? And so the hash must be decrypted with the corresponding key at the other end. And so this is going to prove the identity of the sender. And so digital signatures, the term we use here is non-repudiation, or sometimes we just say authenticity. They can be used synonymously. And also message integrity, right, would also work. So non-repudiation means that the sender cannot deny that the message came from them. The book gives us on page 311 a good example of one of the early ciphers called the Caesar Cipher, which is just about substituting each letter of the alphabet with a letter 3 positions further down the road. They give you a pretty good example of that here. Now I wanted to give you a picture of digital signatures. And so you notice on the top left, we have this unencrypted message that we've written. And so Gloria creates this message. She wants to send it to Paul. She creates the hash values and calculated from the message, so it gives it a numeric value. And then Gloria, this is using PKI, which we'll talk about here in part 2 of this week. But she's going to, Gloria's going to use her private key to encrypt the hash, right? And then Paul later is going to decrypt the hash using Gloria's public key, which everybody knows, right? And then Paul is actually going to calculate a new hash value and going to compare it with Gloria's hash value that gets sent to confirm that it was from her. So that's kind of a neat picture. Pause the video and study that if you'd like. It's kind of a good summary of how digital signing works using hashing functions. And so then we continue the conversation with types of keys, right? So if we said a key is needed for encryption, how many, so why encrypt at all, right? So encryption protects confidentiality of data at rest and data in transit. Now we can't encrypt everything because it bogs down the system. It's laborious, uses a lot of CPU power, etc., right? So we want to not encrypt everything, but at the same time encrypt many things, right? It's kind of like, in my mind, TCP or UDP, right? Sure, I'd like to know that every packet got there, but do I need to know that every packet got there? Or is sometimes I just want to ensure through TCP that certain packets did arrive, right? So this is, by analogy, I think similar. So encryption can be applied granularly, right, such as to an individual file, or broadly to encrypting all stored data or all transmitted data, right? Per NIST, the appropriate encryption solution for any situation depends on the type of storage, or the amount of information that needs to be protected, or the environments where the storage is located, or the threats you're trying to mitigate. So all these things should come into mind when you're considering the policy that you're going to apply, right? Some of the classes of storage would be data at rest. I call DAR, or I've heard abbreviated DAR, data in transit, or DIM, I call it data in motion. And of course, data at rest, data in motion, data in use is another one. And sometimes we refer to data in the cloud when for your policy considerations. Now, the current standard for encrypting is using AES, or Advanced Encryption Standard. Almost all known attacks against AES as algorithm, its underlying algorithm, are computationally infeasible, the book suggests, and I would agree with that approach. So it will use two types of keys. I also want to mention, before I get to the symmetric and asymmetric, that in addition to being a best practice, encryption is cited in a lot of federal regulations. The Graham-Leach-Bliley Act, GLBA, we've studied here or in other courses, HIPAA, for example. So at the state level, even states mandate some sort of encryption. So you want to consider that in your policy considerations also. So I'm going to take a short break, and then we'll come back and talk about what is a key, key space, some of those definitions we reviewed just a few minutes ago, but now we're going to make them real and dive into symmetric and asymmetric cryptography. See you in just a little bit.